Hello everyone. In this video we will talk about using the definite integral to compute area between curves. So I want you to recall that if we want to find the net change in some function f on a time interval, say from a to b, then we would look at this integral, right, from a to b of its rate of change. So for example, right, we have our common example of distance, right, where f is distance and f prime then is velocity. Then if you take the integral from a to b of your velocity function, this is going to be the net distance traveled over that interval of time. Net distance over the interval from a to b. And so how is this relevant for what we're talking about? Well, you may undergo some drastic change. We're seeing one right now with the coronavirus, where maybe some big instance happens, right? So say we have our economy and it's growing nicely, and then suddenly here we are in month 3, we're in March, and then what would have happened in a normal year is this, and then what happens this year is suddenly we start going down, right? And so maybe you want to figure out, all right, I want to stop my time here in August, and I want to figure out what is the difference, right? Not just what's the rate versus the rate, but like how much money have I lost, right? That would be this area, the net change in the total amount here. And so what we really want is, what is this area? And so we can use integrals to compute this. Okay, so this is kind of our picture, but less marked up from the previous slide. So how do integrals come into play here? Well, we want this black area here. Now, how can we get it? Well, we can take all of the area underneath f, right, in the red here. So we can have this red area, which is exactly the integral of f of x from 3 to 8. That tells us what we would have had. And then we want to subtract away the blue area underneath g, right? So we have our integral from 3 to 8 of g of x. And so basically if you take out the stuff under, you get exactly the stuff between. And so the area between here, or the net change between the two, is the integral from 3 to 8 of f of x minus the integral from 3 to 8 of g of x. And you can simplify this and just write the integral from 3 to 8 of the difference between the functions, right? So take your top function f of x minus the bottom function g of x and take the integral. And this actually happens to be true in general. All right, so this is just the more formal way to say this, and the fact is you actually don't care if they're both above the x-axis, so that's why I drew g below here. So if we call this region R, the thing bounded on the left by a, on the right by b, above by f, and below by g, right? So I've just kind of shaded it in blue here. Then its area is always take the integral from your left bound to your right bound, and then the actual function you will take will be the top function minus your bottom function. Okay? So let's go ahead and look at an actual example with real functions here and not just pictures. All right, so here are two actual functions. So we've got f of x is x squared minus 5x minus 7, some parabola, and g of x is x minus 12, which is a line, and we want to find the area between them from -2 to 5. So first of all, we have a graph, right? We're looking at -2 over here, and we have 5 somewhere over here. And so we need to figure out what is on top, right? And what is on bottom. So unless you already know exactly what they look like or have some graphing tool, the way you want to do this is look for where they intersect one another. So they're going to intersect when they're equal, right? They share a point. And so you're looking to solve for f of x equals g of x. So in this case, that means we write this, and then if you solve a few steps, you see that it solves out nicely. We get 2 roots, and so these guys are going to intersect at the right boundary here at x equals 5, and also somewhere in the middle at x equals 1. And so then we just need to get a few points here. So we know that the parabola goes through, its y-intercept is -7. The line intercepts at -12. And so let's just say I draw f in red and g in blue. Then the easier one to do is g, right? Because it is just a line and it's going to look like this, right? It has slope 1, so by the time it hits 5, it's gone up to -7. And then it goes down over here at, this is -14. And then f, it's going to go through -7 here, and we know at 1, so at the y value -11, it's going to intersect the blue graph. And then we know it comes back up and it intersects again here. And so when we talk about the area between them, we need to see both of these regions. So first of all, let's see where this actually goes up. It's going to go up and hit at 7, right? Because we have 4 plus 10, 14 minus 7 is 7. And so we have two different regions that we're talking about here, right? We have this region over here between them where f is on top. And then in the yellow, we have this region over here where g is on top. And so what do you think we do? Well, we're going to just split our integral right here at 1. So our area between them is going to go from -2 to the intersection point of f minus g plus the integral from 1 to 5 of g minus f, because here f is on top and here g is on top. And then these are both polynomials. It's pretty easy to compute these integrals. I mostly just wanted to show how to set this one up and not necessarily take the time to compute it. So for your first exercise here, I want you to also just set up the integral. You don't necessarily have to figure it all out. That would compute the area between these two curves, both parabolas in this case, on the interval from 1 to 3. All right, so let's do one more example and find the area of the region between x equals 9 minus y squared and x equals 5. So the first thing I want you to notice, right, is we've changed our independent variable and dependent variable, right? Now this is x as a function of y instead of y as a function of x. So you can view things in a couple ways here. So we know what these graphs look like, right? This is x starting at 9 down here, and then it's a downward facing parabola, except for it's not downward, it's leftward, because we have y instead of x, right? Negative x squared would face down, but this is moving horizontally, not vertically. And so we head back left. So this is 9 minus y squared, and then x equals 5 is just a vertical line, right? So we're talking about this region here. And so to find this area, you have a couple of options, and I want to talk about both of them. So you can just do top minus bottom as we did before, right? This is our top in red, and then our bottom here in green is this piece. So here we have to figure out, like, what are these functions, right? Because I was given a function in terms of y, not in terms of x. And so if I want to do like this integral from 5 to 9 of top minus bottom, I have to rewrite these. So this is really just the two pieces of x equals 9 minus y squared, right? You can solve for y as y squared is 9 minus x, and so y is plus or minus the square root of 9 minus x. And so the top is the positive square root, and the bottom is the negative square root. And so that's a little dx there. And so you would end up with the integral from 5 to 9 of 2 times the square root of 9 minus x dx. So this would work. Now it's going to require a little u sub there, and you have to deal with the square root, but it's not too bad, right? But you do have another option. So the other option is to change your perspective. So instead of always thinking of moving with regards to the variable x and then thinking top minus bottom, you can focus on the y-axis instead of the x-axis. And so here, your top, again in the red, would be looking from the perspective of the y-axis, so the top is like the furthest right, and then the left, or the furthest left thing, is going to be your bottom in this case. So if you want something with respect to y, right, you like do a dy, then instead of top minus bottom, it's going to be right minus left. Okay? And this can be useful sometimes, and we'll see why in this case. So you'll get a much easier integral that doesn't require like a u sub or have any square roots. The other issue is we need to find our bounds, right? So for x, we usually go from left to right. So for y, we should be going from bottom to top. So we need to find these intersection points, right? So what are those? Well, that's where 5 is equal to 9 minus y squared, or when y squared is 4. So these are plus or minus 2. So this is negative 2. This is 2. And so these are bounds for our integral. And so when we actually input the functions here, we get 9 minus y squared minus 5. And this is actually just a really nice function, right? This is just a simple quadratic of 4 minus y squared. And so this is much easier to do the integration on. And notice, right, we didn't have to split into like two different functions here. It already was like nicely written as 9 minus y squared. So this is kind of an advantage you can have sometimes when you notice that maybe one axis is preferable to another. So I thought it was worth talking about doing things with the variable y, since we're always so used to doing everything with the x-axis as our main one. All right, so for your second exercise, I want you to use this new method. So I want you to use integration with respect to y to find the area bounded by these two functions. And you're going to have to find the intersection points to figure out what bounds you really need to use here. All right, thank you for watching.